Hi Science 10, welcome to the last part of 4.2, and this is lesson 4 for 4.2, and today we're talking about a little bit more about the laws of thermodynamics, and for this it's one more little formula that explains how much heat is used when you are either freezing, melting, or you are evaporating or condensing some liquid. So calculators are going to be needed for this. We're again looking at two sections in your textbook. We'll be taking a peek at 160 and 161, as well as 380 and 386. So part of chapter 4.2 and part of chapter 10.2 again for this section. There's one page of the notes that has questions for this lesson, and it will be on page 25 of your notes, and there will be 8 questions that you can practice on page 25. Okay, so a couple of review things here. Thermodynamics is the transfer of heat or thermal energy because of motion of moving particles. And reviewing from before, the first law is energy can't be created or destroyed, but transformed from one kind to another kind of energy. And the second law is that there will always be some of the energy lost as heat, so there's never a 100% efficiency whenever there's a transfer of energy or a change from one form to another form. So if you have a light bulb going electricity to light, there's also some waste heat from that you are not intending that light bulb to be, but there's always some heat given off in energy transformations. And we remember that heat is always going from what's warmer, like the room here, to what's cooler, like the ice. And so the energy always goes from the warmer things to the colder things. So the room temperature or the room temperature heat in the particles will go and melt the ice. And what happens is this will continue until there's an equilibrium. So if you leave that glass of ice on the counter for a day, eventually the particles in there will be the same temperature as the particles around them in the room because they will reach an equilibrium. The second law also talks about the fact that heat is always, the hot particles are always the ones that are transferring the energy to the cold, and it would take a lot of energy if you were to get rid of the heat, like in a fridge or freezer. That would take electricity that's working hard to get rid of the heat because the natural flow is for the hot to go into the cold particles. And so we're looking at all the places in an engine where there's energy flowing, hot water sending energy into the metal go into the air into pistons into the moving parts. So there's always those transformations happening. Is the heat getting in if you open your window on a cold day? Sorry, is the heat getting out or the cold getting in? And from this lesson, you know that the answer is this one, where the heat is the one with more motion, so the heat is actually escaping. The cold air that you can feel coming in from the window is just because when the hot air moved out, then there was room for those particles to be replaced by the cold air that are always going to be more down by your feet, and the hot ones are going to be kind of moving out the top of the doorway because of that convection current and hot leaving, but it is hot moving out. Okay, so we talked about the hot substances always being the one moving, and we've seen this state change graph in Science 7 before, but as there are changes in states, there's also some interesting things that will happen here, and that when, for example, you've got ice, water, there's some ice, some water, and it's melting, and if you keep stirring it, as long as there's ice in there, the temperature will stay the same even though you keep warming it up. So it's either in your warm room, or if you have it on a hot plate and you're melting that ice and stirring it, there is no temperature change. It stays the exact same temperature while the melting is happening. So while the state is changing, there is going to be no change in temperature. But once it's all liquid and you keep heating it, it will go up. So it'll stay at 0 the time when it's melting. When it's all melted, the temperature will go up, and if it hits 100 degrees, it'll start boiling. Now the whole time it's boiling though, it will stay at that 100 degrees. And that's because it's changing state again from liquid to gas. So as long as there's some water in there, it's boiling, it's going to be 100. Once there is absolutely no gas in there, let's say you have it enclosed in with some lid on it or something, if it's entirely gas, it will start going up in temperature, and it will be at that spot where the water vapor can get into a higher and higher temperature. So the big idea here is that when the state is changing, there is no temperature change. And the other thing to realize is that there's words for this. As we are melting, that's called fusion. As we are boiling, that's called vaporization. And it's at these two spots, the fusion spot and the vaporization spot, where we can calculate how much heat it takes to do the melting or do the boiling. And there will be a data that we use in order to calculate that for the fusion part and for the vaporization part. So this is our calculation for today, that how much heat it takes to melt a certain amount of substance. First of all, you have to know how many moles of it you have, and you have to know the heat of fusion of that substance. And if you're doing vaporization, you're evaporating something and you want to know how much heat it would take, also you need to know how many moles and what the heat of vaporization value is. So if you go back to your data sheet again, remember that we talked about the heat capacity data sheet. There's also a heat of fusion and heat of vaporization data sheet as well. And so this section tells you the heat of fusion, and of course that would be whether you are melting or freezing, you would use that. And on the other section, we have heat of vaporization. So if you're evaporating something or condensing something, you would use this value. Now, what I do have to point out is that these are both in kilojoules. Your textbook does have an error, and if you are in your textbook and you're taking a peek at their data table, there's an error that science teachers know about. It's on page 381. There is an error on page 381 that says that the heat of fusion is in joules. That is not correct. They are both in kilojoules. So what I do have to warn you about is that that error got transferred into some of the data sheets, and in your note package, your data sheet may have this is in joules for vaporization. But I do want to tell you that all of the numbers are correct, but they are both in kilojoules. And remember, you use heat of vaporization data for melting or freezing questions, and you use heat of vaporization data for evaporating or condensing questions. So going back to this last part of our lesson today, our heat energy will always be calculated in kilojoules. We will find out how many moles of whatever substance they're talking about. Heat of fusion will always be in kilojoules per mole, and heat of vaporization will always be in kilojoules per mole. So those need to be corrected as you do look at the units that we'll be using for this. So we're just looking at how much, for example, to melt something here, it would be heat of fusion. How much energy to freeze it again, still heat of fusion. If it was talking about evaporating it, we would use heat of vaporization. So in this case, we're talking about having it vaporize or evaporate. This would be heat of vaporization. Same with taking that liquid water and condensing it again. Condensation is also heat of vaporization. So make sure you remember the melting freezing is fusion, the evaporating condensing is heat of vaporization. So when we talked about this transformation chart before, remember that ice and water, when we're melting or freezing, it's heat of fusion. When we're talking about liquid to water vapor, it's evaporating and condensing is heat of vaporization. You can see it on this picture really nicely. The word sublimation, when we go directly from ice to vapor or water vapor to ice, remember that definition. We're not doing calculations on that though. And the reminder here about moles is that for these two formulas you will need moles, and you will have to remember that moles are determined by the mass that's given in the question divided by molar mass of whatever substance they are talking about. So you will still have to use mass over molar mass to do the following examples. So a heat of vaporization example here, it tells you that they give you grams, they tell you it's water, they tell you that it is looking at converting liquid to water vapor. So you know that you're using the heat of vaporization because you're turning it into water vapor. So you know which part of your data chart to use. And it's a two-part question. You do have to find the mass over molar mass to give you moles. And so the mass in the question was 360.4. The molar mass is just molar mass of water. Remember that 2 hydrogens is 2 times 101. Check your periodic table. 1 oxygen is 1 times 16, and it will end up being 1802 grams per mole. And you just put that in your calculation and find out that your moles is 20.00. Now you can actually do this calculation. You've got the 20.0 as your moles. And the heat of vaporization, the 40.65, everyone, is, again, going back to your data table, you're going to be able to find it right here. The heat of vaporization of water is 40.65. So that is where you're going to get the data in order to determine your final answer. And because that is in kilojoules, don't forget that the final unit that is given will be in kilojoules. So it is final answer 813.0 in kilojoules. So that is an example of how we use the heat of vaporization and heat of fusion formulas. Remember that you're going to have to determine your your moles by doing mass over molar mass and finding your vaporization in the data table for anything that's talking about evaporating or condensing. If you're looking for the value for anything that is melting or freezing, you're going to go moles times the heat of fusion for melting or freezing. So those are the two possible kinds of examples. So give those a try. Your assignment there on page 25, the 5 questions, and check the key.